Assalamualaikum and good day everyone. My name is Idham Arif alias from University Putra Malaysia, and this work is a collaboration between me and my master student Karun Zaman, and also with my fellow colleague at UPM, Associate Professor Dr. Ghafurjan Ibrahimov. So our project here is about a pursuit division game that happened in a convex hyperspace consists of many pursuers against one evader as suggested by this title. Okay, the motivation of this research is to improve a guaranteed pursuit time from a previous work, and where guaranteed pursuit time means that a time where pursuit is guaranteed to be completed. So that's our motivation. And in doing so, for this project, we introduced a new approach of how to apply parallel strategy that being used by pursuers to capture the evader. Parallel strategy is a standard strategy for pursuers to capture evaders, which was introduced by Petrosyan in in a few years back. Okay, then also besides introducing a new method to apply the parallel strategy, we also use the concept of fictitious pursuers, where this concept was used by Ibrahimov and Satimov in 2012. Okay, so before we proceed to our result, let's have a quick look at the literature review or introduction. So, differential game is a game which is described by some differential equation. The movement of players are described by some ordinary differential equation. And it is about constructing a strategy for the players in focus. For example, if it is a pursuit game, so the problem is to construct a strategy for pursuers where the movement of evader is free or can be anything. So this kind of pursuit game is listed here, for example. And on the other hand, if the player on focus or in focus is evader, so the problem is to construct strategy for the evader where the movement of pursuers could be any, meaning that pursuers can move freely. So this kind of evasion game, for example, are listed in this reference. Now, again, movement of players are controlled by control function. It means that player can only move with a control function. It is like an engine for player to use to move. So this control function of players can either be limited by some kind of constraint. It could be geometric constraint, for example, which are discussed in this following list of words, or it could be the constraint could be limited by integral constraint, which are studied in this, for example, in these words. Geometric constraint is some kind of constraint that limit the speed of players, while integral constraint are some kind of constraint that limit the resource, usually the energy of the players. Okay, now also differential game can be specified to be studied in some kind of space. For example, in Hilbert space, which are studied in this following list. Or also could be studied in Euclidean space Rn, for example, in this list of words. So in our work, we study in a convex space, which is a subset of Rn. And for this more specific work, where the game is in convex space. So here are some explanation about, or some a little bit more details about what was done in this following list of work, which is in the convex space, which is about our project, which is similar to our project. But again, there might be not a smooth flow between all these five. I mean, maybe some of this work are independent of each other, even though they study the game in convex space. But the one that which is closely related to our project is this one, where a guaranteed pursuit time is given as this. And then this guaranteed pursuit time is then improved by a work in 2015, where the guaranteed pursuit time is improved to be this one. So now our project is to improve this guaranteed pursuit time. Okay, so now we go to our two main results. First the definition, but first the first result is where we study pursuit game in a set that contain a closed compact set. So say that this closed compact set is S, and the set that contain S is M. And what we prove here is we get two results here, which are theorem 1, which says that a pursuit can be completed in the superset of S, which is M. And the second theorem says that the guaranteed pursuit time for the pursuit game in S and in M are actually the same. Even though S is a subset of M, but the guaranteed pursuit time in those two, in this M and this S, are actually the same, even though S is a subset of M. Okay, these two results are achieved by using fictitious pursuers, and where we define a function that link between the real pursuer and the fictitious pursuer, which is described by tree. And then this function is defined by equation 4. So tree link between the real pursuer and the fictitious pursuer, and the function is described further by 4. So by using these two, we can prove those two results. Now we move to our second result, which is where we study pursuit game in n-dimensional cube, which is a happy cube, where we define as follows. So this is so the dimension is n, and the cube that we define in our project is different from the one in the previous work in 2015, where we want to improve the guaranteed pursuit time, where the origin of this n is where the center of this n is the origin, but the center of the cube in the previous work is not the origin. Okay, so and this is the result that we get, the improved guaranteed pursuit time that we obtain in this part. And we obtain this by introducing a new approach to apply parallel strategy for pursuers in the pursuit game in this cube. And it consists of two stages. In stage 1, because pursuers are all over the cube at the beginning, at time 0. So for the stage 1, all pursuers move towards the origin of the cube. So that's the first one. And for the second stage, the central idea of this second of this part is stage two, where from the origin, the pursuer is starting to move to capture the evader. But instead of catching the evader by moving on the side of the cube, as in the previous work in 2015, we introduce the movement of pursuers is to catch the projection of the evader in this another hypercube, but which has dimension less than 1 from n. So what happened is the pursuers will catch the evader, will catch the projection of the evader on this qi and proceed to catch the evader within n afterwards. Okay, so by this method, but the movement is always parallel strategy. But the way we determine how this parallel strategy is used is by what we have described before. So now, so from those two, we obtain our guaranteed pursuit time, as we saw in theorem 3 just now, which is this. And then from these two stages, we get our main result, which is theorem 4. This theorem 4, which is our main result, is just the same as the guaranteed pursuit time in theorem 3. But we use the idea of theorem 1 and theorem 2 because this S is contained in N. And because of that, the guaranteed pursuit time in S is just the same as the guaranteed pursuit time in N. Okay, I think so that's our project is all about. And thank you for listening. And this is the list. This project is thank you to the FRGS for supporting this project. And this is the list of reference. Thank you very much, everyone.